Can you hear me now? Is it clear?
Yes, sir.
Yeah. Now, in this today's lecture, let us start learning about what is meant by operational amplifier and how that particular operational amplifier is being used as an adder and also as a subtractor in its differential configuration. So now here also we'll be designing an op-amp in a differential configuration, and that particular op-amp which is designed in the differential configuration will be used as an adder and also subtractor. Let us see that one now. So see here now. Here I have a circuit where which I have named it as a difference amplifier. Here, difference amplifier, we all know that this circuit we have studied in the early classes about what is meant by differential amplifier. It's the same 741 circuit op amp where you could see there are two inputs V1 and V2, and this it is having one RF here. That RF is a feedback resistor that is connected to the output, and at the input at the non-inverting terminal we are having R1 and RF, another compensating resistor over here, and V1 and V2 are my input voltages. So let us now enter into this particular concept of how this particular differential configuration based op amp can be used as an adder and also subtractor. So let us see the case number 1. Here in this particular circuit, what we are going to do is that we are going to apply the superposition theorem. We know what is meant by superposition theorem. In the superposition theorem, only at one time one of the particular voltage source will be acting and other one will be grounded. So that is a superposition theorem. Only one voltage source will be acting and other one will be grounded. So the same thing we are going to do here in the first case. Case number 1. When V2 is acting, means we are making this V2 as an applied input voltage source to the op amp, and then V1 is grounded, then V1 should be connected to ground. If V1 is connected to ground, and only the V2 voltage source will be connected over here. If that is the case, my circuit is being converted into this fashion. You can see here now, my V1 is directly connected to ground. That means that the voltage at the ground is equal to 0 volts, and the rest of the circuit is similar to the previous one, which you find in here in this particular place. So now here we are supposed to find it out what is the voltage which is present at the VA. Why we are talking about VA here? Because since my voltage which is connected over here is a 0 volts, and this is my input voltage which is directly supplied to my op amp. See, most of you might be in a confusion mode regarding which kind of inputs the op amp will be taking. Actually, the op amp will be taking the inputs which are connected to this terminal itself. It is not bothered about what kind of inputs you are supplying at this V1 and V2. It is bothered about what kind of input voltage is being applied at inverting terminal and non-inverting terminal. So that is the most important part everyone should understand. This here we are supposed to understand what kind of input we are applying here at VA and VB. So that's why we are going to calculate what is the voltage VA across this RF. This voltage we are supposed to calculate. What amount of voltage will be across RF? That is my VA. So how that can be done? That particular calculation of this voltage across RF can be done by using a method called voltage division method. It can be done by using what? Voltage division method. What is voltage division method? We know that is RF upon R1 plus RF into the voltage source. What is the voltage source? It is a ground voltage. So that thing we will be applying here. See now. Here now, when we apply the voltage division method, your circuit, the voltage at this VA is equal to RF upon the sum of these voltages into the voltage source. So this becomes my equation, that is VA equal to RF upon R1 plus RF into 0 volts. So when I apply 0 volts into this particular fractional term, I'll be getting VA equal to 0. If VA equal to 0, if I substitute VA equal to 0 over here at this particular part, my circuit looks like this. I'll be having only V2. R1 is my resistor which is connected between the inverting terminal and the V2. and I have got also one feedback resistor RF, and this particular non-inverting terminal will be connected to ground. So now this particular circuit is looking like similar to your inverting amplifier which we have studied. So the gain of inverting amplifier, we know what is the gain, that is minus RF upon R1. It is minus RF upon R1, that is my gain. So my AF is equal to, what is AF? It's a gain of this particular circuit, that is equal to V out upon V in, that is equal to minus RF upon R1. So I can write now my V out is equal to, if I send my V in to this side, it becomes V out equal to minus RF upon R1 into V in. So my entire equation of my output voltage in this particular case 1 will be equal to minus RF upon R1 into V2. So this is done by what? Whenever the V2 is acting, means whenever the V2 is connected. Now this is a first case of your this is a first case of your superposition theorem. This is a first case of your superposition theorem. So this is how you will be applying your superposition theorem for the first case. Someone must be joining. Okay, can you see this one now? Is it clear? Can you see it?
Yes, sir.
Yeah, okay, fine, ma'am. So this is your circuit equation of V out. Now we have found out the value of V out whenever the V2 is acting by using a superposition theorem. That's the case number 1. Now let us enter to the case number 2. See my case number 2. In the case number 2, what I told just now, we will be applying the superposition theorem, means what? Only at one time we are going to make one voltage to be acting and the other voltage is going to be grounded. So in the first case, we have made V2 to be acting and V1 was grounded. Now what's the second case? In the second case, when V1 is acting, then V2 is grounded. So you can see my circuit diagram over here. This is my circuit diagram. Whenever this is acting, now this particular circuit looks like your non-inverting amplifier. It looks like your non-inverting amplifier which you already studied. And again, in this case, again now I'll be applying my voltage division method to find out what is the voltage again at VA. See, always keep in your mind, while calculating this calculations, you are going to find out only the VA. You are going to find out the voltage at this part only. Why? Because now this is making as a node. This particular node only you will be calculating only VA. Don't think that VB will be calculated. Why VB is not calculated? Because we are supposed to apply the virtual ground technique. What is the virtual ground technique? We know that whatever the voltage is over here, the same voltage will also exist over here. Why? Because internally these two terminals are connected. These two terminals are connected. That's a virtual ground or virtual short concept. So because of that one, whenever we get the value of VA, the same value exists at the VB also. So that's why we are only calculating this VA here. Don't think that why we are calculating only VA every time. We are calculating VA only because we know that by using because of the virtual ground concept, whatever the value you get VA, that will be equal to VB. Now let us apply the voltage division method at this node, that is VA. If I apply the virtual ground, voltage division method here, I'll be getting the value of this RF upon sum of these two, R1 plus RF, into the voltage. What is the voltage here? That's the voltage is V1. So now it becomes VA equal to RF upon RF plus R1 into V1. Now this above circuit, it becomes as this circuit. You can see now this circuit is directly connected. Now this is nothing else but it's a non-inverting amplifier. So now this is looking like just like your non-inverting amplifier, where I have removed this one. Why? Because ultimately this is the main voltage which your op-amp will be taking. It's not the voltage which is coming from this V1. It is a voltage which is present over here. That is, the VA is most important. These two nodes are most important. Why? Because these two nodes are directly connected to the op-amp. The op-amp, even if you talk about a differential amplifier, your differential amplifier also will find out the difference of these two voltage nodes only. It will not find out the difference of the voltages which are connected here as V1 and V2. It will find out the difference of these two voltages which are directly connected to the op amp. So that's the most important thing which you are supposed to keep in your mind. So that's why I have written here my VA equal to Vin. My input voltage will become as Vin, that is VA. So this is now a non-inverting amplifier. We know the formula for the non-inverting amplifier's gain, that is AV equal to 1 plus RF upon R1. So this is how we found out the some part of the case 2, and now we will try to solve this equation in order to find out the output voltage VO. That is AV equal to, we have found out what we have found out here, AV equal to 1 plus RF upon R1. In place of AV I can write it as VO, that is V out upon Vin. So that's why V out upon Vin equal to 1 plus RF upon R1, and that is, if I send this V1 to this side, cross multiply, it becomes V out equal to 1 plus RF upon R1 into VA. Why we are writing in place of VA here? Because I have told you earlier here my VA equal to Vin. This is my actual input voltage. So that's why it is Vn equal to VA. So now I'll try to substitute the value of VA. Already we have found out what is the VA in the other concept. Previous slides we have found out what is VA. That VA equal to RF upon RF plus R1 into V1. That value I have substituted over here. If I substitute this value, you know that these two will get cancelled. Ultimately, I'll be having my output voltage is equal to RF upon R1 into V1. So this is when this is the output voltage of your this particular amplifier whenever the V1 is acting. Whenever the V1 is acting. So now this equation we'll be applying the superposition theorem. What is the superposition theorem? Superposition theorem tells that what is the total output, what is the total voltage when all the voltage sources are acting is equal to what is the total, what is the voltage when individual voltage sources are acting. That is equal to the total voltage is equal to V1 plus V2. So that's why we have written here. Now by superposition theorem, V out is equal to V out of the inverting amplifier stage plus V out of the non-inverting amplifier stage. So these two we have already found out in the previous cases. That's how you get V out equal to minus RF upon R1 into V2. This is for the non-inverting case you have found out over here. This case I am talking about this one, minus RF upon R1 into V2. This is a non-inverting amplifier. And for the invert, this one we have found over here. This is for the inverting amplifier. And for the non-inverting amplifier, you have got the value of V out equal to RF upon R1 into V1. So that particular values we have substituted over here. If you substitute in this place, you will get V out equal to minus RF upon R1 into V2 plus RF upon R1 into V1. Now we will take the common of this RF by R1. If you take a common, it will be written as V out equal to RF upon R1 into V1 minus V2. This is called as an difference amplifier output. This output we call it as an difference amplifier output. Now your particular op amp which you have seen in the first case here, this particular op amp is now acting as a difference amplifier after undergoing the superposition theorem concept. So now whenever this particular gain is equal to 1, RF upon R1, whenever this amplifying factor is equal to 1, then your particular circuit will be called as a subtractor. That's why your output becomes, if I substitute in place of RF upon R1, 1, your circuit becomes, the formula of this circuit becomes V out equal to V1 minus V2. So that is nothing else but subtraction. So that's why I can call this particular circuit as a, not as a differential amplifier, I can call it as a difference amplifier. Why? Because it is finding the difference between these two voltages. It is finding the difference between these two voltages. Ultimately, I'll be calling it as a difference amplifier. This is about how your particular circuit can be converted. Op amp is been working as a difference amplifier. Now let us see the other circuit where your op amp can also be used as an adder for addition purposes. So now this is a circuit which I have taken. That's why I have named it as second circuit method. In the second circuit method, just like what we have studied in the previous lectures, where we have connected 2 or 3 resistors at one particular nodes. Okay. Now this circuit is what, ma? So this is about adder-subtractor using op amp differential configuration. This is about adder-subtractor using op-amp differential configuration. So now you can see here now there are four voltage sources here, V1, V2, V3, V4, where V1 and V2 are connected to the inverting terminal, and V3 and V4 are connected to the non-inverting terminal. If you look into this particular diagram, all these resistors are of same value. All these resistors are of same value. Now let me assume that if the voltage source is connected over here and that particular voltage source is directly connected to resistor, then definitely there will be some amount of current flowing through all the resistors from this voltage source. Let that current is equal to, from this one is equal to I4, from this one equal to I5, and this is equal to, now see now the I4 and I5 will be coming in the same direction. It is forming combining at this particular nodes. So whatever the current goes out of this one, it is equal to I, that I is equal to I4 plus I5. In the similar way, here also you will be having two currents, that is equal to I call it as here you will be having like three currents, that is I call it as I1, I2, and this one I will be calling it as I3. So the current flowing through this resistor which is connected to voltage source 3 is I1. The current flowing through the resistor which is connected to voltage source V4 is equal to I2, and the current which is flowing through the node VA, flowing from the node VA through resistor is I3. So now how to find out what is the concept of this one, how to find out the voltage, let us see now. Now first one, for this one, firstly let us apply the virtual ground concept. We all know what, just now we have seen what is a virtual ground concept. What is a virtual ground concept? Whatever the voltage is present over here, the same voltage also exists at this particular node. Why does it exist? Because internally we know that through one particular resistor, these both are directly shorted, or both these are directly connected. Because that concept we call it as an virtual ground or virtual short concept. So now here, since they are directly connected, we call it as a virtual ground or virtual short concept. Because of that one, you can see here now the voltage at this one I am naming initially as a V plus, that V plus equal to V minus. The voltage is equal to, initially I have named it as V plus and V minus, that V plus equal to V minus, that is equal to VA equal to VB. Now we can draw this part. See now what I have drawn in the dotted line. I am trying to redraw the diagram as this one, so that we can understand the concept of how to find out what is the voltage at this node VA. I need to find out the voltage, because just now I have told that by using the virtual ground concept, this both VA and VB will be same. But now I need to find what is the voltage at VA first. So for that one, I'm redrawing this particular diagram as this one. Here you can see in place of V3 I have connected one voltage source, and the negative terminal is connected to ground. And in place of V4, you can see here now I have connected one voltage source, that's V4, and the negative terminal is connected to ground. And this one, this resistors, anyway the one another terminal is connected to ground. So it means that all these two voltage source negative terminals and this one is connected to ground. So I'll be getting this circuit. So you can see here now these two will be acting as a principal nodes. These two will be acting as principal node, and this one will be taking I'm trying to explain you what is meant by nodal analysis. I'm trying to explain you what is meant by nodal analysis. In the nodal analysis, you have studied that you'll be having the principal nodes, and also you'll be having a reference node. The node which is connected here, this one I'm considering to be my reference node. I'm considering this to be my reference node, and this is going to become my principal node. And here, see here, V plus. What is V plus ma? This V plus equal to, I have told here, V plus equal to V minus, that is equal to V plus is nothing else but VA. So I have taken this node value, the voltage at this node equal to VA. So let us now apply the nodal analysis for this circuit. So see here now, by using a nodal analysis, here the potential at the principal node is considered the largest potential. Using the principle of this one, we know that the potential at this one will be considered as the largest node. The principal node potential, we know that as per nodal analysis, the potential of a principal node will be always considered as the largest node. That's why we call it as a principal node. Why? Because its potential is larger than all the other nodes. So that's why here the potential at the principal node is considered the largest potential node. That's why I'll be getting both are directly connected without any passive element. Both are directly connected without any passive element. Whatever the voltage is present over here will be the same voltage here. So that's why this node also will be equal to VA. That's why now the VA plus equal to VA. Each branch will be having the currents which are flowing. That's what I have talked here. Each branch is having the current which are flowing. The current flowing through this one is I1, the current flowing through this one is I2, and the current flowing through this one is I3. So this one, now we'll apply the nodal analysis. What does the nodal analysis tells? Now the sum of all the total currents, the sum of all the currents at any node is equal to 0. We know that nodal analysis, the sum of all the currents is equal to 0. The algebraic sum of all the currents at any node is equal to 0. So that principle I have applied here. I1 plus I2 plus I3 equal to 0. The current which are flowing here, all these currents, I1 plus I2 plus I3, these are coming from this particular node. I am assuming that the current at this node is equal to 0 now. So that's why it is equal to I1 plus I2 plus I3 equal to 0. Now I will be writing this one in terms of V and R by using the Ohm's law. I will apply the Ohm's law over here. So now if I apply the Ohm's law, you can see now here, see the direction here. Since my current is flowing from the VA, my current is flowing from the VA to V3. That's why I should always consider your current always flows from where? Higher potential point to the lower potential point. The current always flows from the higher potential point to lower potential point. It means what? If your current is flowing from VA to V3, or current is flowing from VA to V4, or current is flowing from this one through this resistor, means what? The current which is VA, this is much greater. This particular voltage, the voltage which is over here is much greater than the voltage here in this 2 voltage. That's why I'll apply now nodal analysis. What is nodal analysis? I'll be applying the nodal analysis, this one, and now I1 is equal to what? I1 is equal to VA minus V3. VA minus V3 upon R. In the same way, I2 is what? VA minus V4 upon R. Then what is this I3? I2 is equal to VA minus V4 upon R, and I3 equal to VA minus, there is no voltage source, it is directly connected to ground. So that's why it is VA minus 0 upon R. You can see now, VA minus V3 upon R plus VA minus V4 upon R plus VA minus 0 is nothing else but VA only. So it is VA upon R is equal to 0. Now we will try to simplify the circuit. When you simplify the circuit, you will get VA equal to V3 plus V4 upon 3. Now we have found out what is the value of VA. What is the value of VA, ma? The value of VA just now we have got VA is equal to V3 plus V4 upon 3. This is my voltage at node A. That's now as per the virtual ground, what I told, whatever the voltage is present over here will be the same voltage present at this one. So now VA equal to V3 plus V4 upon 3. The same voltage is present also at the VB. So that's why I have written now VB is equal to VB equal to VA as per the virtual ground concept. Now let us assume the current which is flowing here from the V1. The current which is flowing from the V1 is equal to, so see now. Are you following me? Is it clear?
Yes, sir.
Is it clear, ma? Okay, see now. Okay, now let us see. Let the current flowing from V1 is V4. Just now in the previous class, the previous concept of this particular first graph, first diagram I have told, the current which is flowing from this one is V4. The current which is flowing from this V2 is I5. So the same thing I have written. The current flowing from V1 is V4 and the current flowing from V2 is I5. Now I need to find out what is V4 and I5. Sorry, what is I4 and I5. Then how to find out I4 and I5? Just like what we have done here for this one. Just like how we found out I1, I2 and I3, we'll try to find out this one. So see now, the current is flowing here. The current is flowing from V1 and it is going into this node VB. So it will be what, ma? The current which is flowing here is equal to V1 minus VB upon R. See, always consider why I should take V1 minus VB, because why I'll be taking, okay, VB is nothing else but VA only. Ultimately I'll write it as VA. So why I should take it as V1 minus VB, because your current always flows from the higher potential point to the lower potential point. If current is flowing from V1 towards VB, means what? V1 is much greater than the potential at VB. So that's why you should always take this as V1 minus VB divided by this R. And again, the current which is flowing, that is I5 is equal to what? I5 is equal to V2 minus VB divided by this R. So now we have found out I4 equal to V1 minus VB divided by R, and I5 is equal to V2 minus VB upon R. The same value we will find here. So see now, I4 equal to V1 minus VB. What is actual VB? VB equal to VA as per the virtual ground. So that's why I have written directly V1 minus VB upon R is equal to, what is VA? We have already calculated the VA. VA equal to V3 plus V4 by 3. So substitute over here. V1 minus V3 plus V4 by 3 divided by R. In the same way, I5 equal to V2 minus VA upon R is equal to V2 minus, what is VA? This value. Substitute over here. When you substitute and do some simplifications, you will get these equations. Now, so see now, as we know that I is equal to I4 plus I5. I have told in the initial point itself, the two currents are flowing into this node, and that one current is flowing out. Means what? The current entering the node is equal to current leaving the node. That's the what is the current at this particular node? We have studied KCL. KCL equal to the current entering the node is equal to current leaving the node. Now we'll be applying the KCL concept. The current entering the node is what? I4, and I5 is entering the node VB. And what is the current which is leaving? That's the I. So that's why I have written I equal to I4 plus I5. So you can see now. As per the KCL, I is equal to I4 plus I5. Now you substitute the value of I4. What is the value of I4? Here we have got. This is the value of I4. This is the value of I5. Now let us substitute that one here. I1 equal to that I4 value, and I2 is equal to I5 equal to this value. When you do simplification here, now you will be getting this value. So see now. Ultimately, after doing some simplification, you will get I is equal to VA minus V out upon R. So what is this I? I'm not talking about this value. I'm not doing the simplifications over here. I'm trying to find out my entire equation. This equation I'm trying to bring in terms of V and R. Means I need to find out what is the value of I on the LHS. So see now, what is the value of I on the LHS? So see now, what is this value of I ma? This I value is equal to what? It is flowing from this point to V out. It is flowing from what? From VB to V out. So you should find out what is the value of I. So this value is equal to VB minus V out divided by R. VB is what? VA. So it becomes VA minus V out divided by R. So here you got, now I equal to VA minus V out divided by R. That is equal to, if I do one small here, I'll get VA minus V out is equal to I into R. So this is that particular diagram I have drawn, how the current is flowing in this one. This particular resistor represents this one. VA is over here, that is nothing else but VB is there in that one. VB equal to VA as per virtual ground concept. So VA, from VA the current is flowing through the R and it's going to V out. So that's why we have written this formula I equal to VA minus V out upon R. If you do some multiplications, you will get VA minus V out equal to I into R. So now you have got this formula. What is VA again? VA we have found out in the previous case. VA equal to V3 plus V4 upon 3. This value you will substitute again here, where VA equal to V3 plus V4 upon 3. That you substitute on the LHS side. Already you have substituted on the RHS side. If you do now simple multiplications, ultimately you will come to one particular point that here V out is equal to V3 plus V4 minus V1 plus V2. So you can see now I have done all the simplifications. You can go through this one. You can see now V out equal to V3 plus V4 minus V1 plus V2. So these two is acting as an adders. It is adding the two particular input signals, and it is also doing the subtraction of those two signals. Why? Because this two signal V3, you can see now. You remember this one, V3 plus V4 here, and here it is V1 plus V2. These are the two same voltage sources which we have connected to either to the inverting terminal or else to the non-inverting terminals. We will be not connecting V1 and V3 or V2 and V4 to the inverting or non-inverting terminals. We will be connecting either V1 plus V2 or V3 plus V4 for any of terminal. Either it can be uh, inverting and non-inverting terminal. So you can see my diagram here. So here V1 and V2 is connected to the inverting terminal and V3 and V4 are connected to non-inverting terminal. So now that's why this is adding the two inputs which is connected, and it is also subtracting those two. Where does this 2 goes? This 2 goes to the nodes of V and VB. So what it is doing at the same time that this 2 will be added up and it will be brought at node B, and this 2 will be added up and it will be brought at the node A. So it is adding simultaneously, it is adding these two signals, and also it is doing the subtraction of these two signals, that is VA minus VB. What is VA? VA equal to addition of these two, V3 plus V4. What is VB here? The voltage will be V1 plus V2. So now your circuit is acting as an adder and also subtractor. Now you are supposed to keep one thing in your mind. If you want to get only in non-inverting adder and subtractor, if you want to get non-inverting adder, if you want to get a non-inverting adder, what you will be doing? These two V1 and V2 will be grounded. These two voltage source will be grounded. So ultimately the voltage here will be directly grounded over here, and it will be only V3 plus V4. If you want to get only inverting adder, if you want to get an inverting adder by using this differential configuration, what you are supposed to do? You should ground this two, V3 and V4 should be grounded. Then I will be getting only V1 plus V2. You can see now. If I want to get non-inverting, what I will be doing? I will be making this V1 and V2 0. If I want to get inverting adder, if I want to get inverting adder means what? I will be making the voltage which are connected to non-inverting 0. So then it will be only V1 plus V2, and it is inverting. It's inverting. That's why I'll be having 0. That's why I'll be having minus here. If I need a non-inverting, this entire terms become 0, and this will be it will be positive term. But if I need the inverting adder, this term will become 0 and it will be having a minus in front of that one. So that's nothing else but simple inverting amplifier circuit. So this is about your op-amp acting as a adder or subtractor, adder slash subtractor in a differential configuration. Have you understood this one?
Yes, sir.
Is it clear?